This is the second video about the philosophy of evidence. I want to remind you to judge things for yourself. Don't take my word for them. This time we're going to talk about science in particular. So we want to know about what sort of experiments are going to produce evidence that will be useful for science. And we want to know something about what would make a new scientific theory be any good, and what that has to do with evidence. So we'll start with an example. Suppose we have two theories. First one, all balls are red. The second one, all balls are green. So what kind of experiment would we need to do that would help us learn about these theories? So both of the theories make predictions about balls, and those predictions disagree. So if you think about any given ball, the first theory was predicting it'll be red. The second one was predicting it'll be green, but it can't be both. They both mean a solid color. So all we have to do is get any ball and look at it, and it'll either be red or green or some other color. So at least one of the theories will get ruled out. They can't both be right. So if we do that experiment, then we're guaranteed to make progress. We will learn something about the theories. So that illustrates how you want to design experiments. First, you need some sort of theories that you're investigating. Then you look for some way that they disagree with each other. Then you want to set up the experiment to test out whatever they disagreed about. Because then whatever result you get, at least one of them will disagree with it. So then one of the theories will be wrong, or maybe both of them. So let's look at a real-life example, which was Einstein's theory of relativity. So before his theory, there was Newtonian mechanics, which was a theory of physics by Isaac Newton. And it was a really good theory for its time. Everyone was very impressed with it. It made a lot of accurate predictions about gravity and about the planets. And one of the things it said is that the sun would deflect light that goes by it. Relativity came along, and it predicted the same thing, except the sun would deflect the light more. So they disagreed about how much deflection there would be. So in 1919, astronomers actually measured the deflection. They waited for a solar eclipse, and then they did observations from two different cities to try and be really accurate, and they measured it. And it turned out that relativity was right, and Newtonian mechanics was wrong, so we had learned something important there. Now we're going to consider a different aspect using relativity again to illustrate something else about how theories need to interact with evidence. So, in 1859, astronomers noticed there was a problem with Mercury's precession. And that's before relativity existed, back when Newtonian mechanics was the theory. So, they had their theory, but they noticed this one piece of evidence didn't fit with their theory, which was a big problem. And precession, by the way, it has to do with how planets tilt while they're going around the sun. I don't know exactly what it means, but it's not really important here. So they had this observation about Mercury, and it was a problem. But when relativity was invented, it actually predicted the correct precession for Mercury. So, compared to Newtonian mechanics, relativity had an advantage because it was getting the evidence right in this Mercury case. But what relativity also had is that it accounted for all the other experiments that people had ever done, which is a really important thing to keep in mind. Because you can invent a new theory that would account for Mercury, and that's not hard at all if that's the only piece of evidence that you want to be compatible with. But what relativity does is it's compatible with all the old evidence and Mercury. And it's really hard to invent a theory like that agrees with all the different evidence. But when we get one, that's great. Then we have a theory that's really worth investigating. So new theories need to agree with all the old pieces of evidence. Otherwise, they would be contradicted by the evidence and they'd be wrong. But if they can also account for some sort of new evidence that the existing theories were having trouble with, then they have an advantage. So that means new theories are hard to come up with because there's so many restrictions. You have to pay attention to all the science experiments we've done in the past. But if you can do that, then you have a pretty good theory that's worth investigating. So to summarize what we've talked about, you should design science experiments to look at the disagreements between theories. That way, at least one theory will have to be ruled out. And when you want to make a new theory to investigate, it needs to agree with all the past evidence, which is pretty hard, but it's worth doing. Bearing in mind principles like this, which aren't that hard to understand, you can look at the history of science, and a lot of it will make sense to you. It really does use fairly simple ideas like this. Of course, they also have to do things like figure out how to observe light being deflected by the sun, and they have to do a lot of math. But as far as the philosophy aspect of things, and the general principles of the debate, you can follow along. This is really how it works.